I'd like to present you today the monitoring that we established in order to study the recharge of karst aquifers. And the reason for that is because we are facing the changed hydrometeorological parameters and more intensive hydrological patterns, and also some natural disasters which are causing the large-scale forest disturbances, and in consequence to that, changes in hydrological cycles, in cycles of CO2, nutrient cycles, and so on. And the most vulnerable environments in this sense are the karst areas, because so these are the areas where soluble rocks prevail, such as limestones and dolomites, and peculiar geomorphological forms occur, for example, sinking rivers on the surface and caves in the underground. And that is why also the flow of the water, the infiltration of water is very fast in these environments, and we can also observe in the human time scale the changes that large-scale forest disturbances can cause. And also we can observe, or we are afraid of, differences in karstification degrees and in deposition of speleothems in caves and processes like that. In 2014, in Slovenia, a very big ice storm occurred, which caused damage of half of our forests. The forests were partly or totally destroyed, and a lot of these areas were underlain by carbonate rocks, by karst aquifers. That is why we were afraid, or we asked ourselves if this may cause differences in the recharge of these aquifers, because this is what I was looking for. This is the map of the world global distribution of karst aquifers in pink. About 15% of the world is underlain by karst, and a third of that is covered by forest in green patches. And you can see that these areas are distributed all over the globe in southern and northern hemisphere, and also in different altitudes as well. And these aquifers are not only important for peak biodiversity, but also as water resources and as other ecosystem services such as CO2 sequestration. And because we were afraid what kind of consequences large-scale forest disturbances can cause, we selected a test site in southwestern Slovenia, where we first took into account some trend analysis of the hydrometeorological parameters, because no specific monitoring was available to calculate the recharge. And comparing the period 1962 to 2018 with the period 2014 to 2018, we observed that the precipitation increased by 3%. And also temperature increased, and consequently the evapotranspiration increased for almost 15%. And the spring that is draining the selected area decreased only minimally, just minus 0.4%, so really negligible, while we expected that the spring discharge will decrease by almost 7%. And by modeling, using soil-water balancing model, it showed us that in the period following the large-scale forest disturbances, the effective precipitation increased for 5%, which is due to less canopy interception and also larger evapotranspiration. And that is why the observed spring was, the discharge of the observed spring was much smaller than expected. But these were only trend analysis and modeling, and we really didn't have any data from the field. And karst aquifers are unique in this sense because they have caves. Some caves are accessible by human, and we can also monitor the recharge within the caves. And the purpose of this presentation now is not to discuss so much about the results, but about the monitoring that we established. Not only monitoring hydrometeorological parameters on the surface, but we also went in the underground and observed the dripping in the caves, not only dripping, but also the sinking rivers. We were not only concerned in the specific plot scale, but we also established the monitoring taking into account different geomorphological characteristics in the area, such as bottom of the downlines, these depressions, or top of the downlines, and we also were interested how forest development is impacting the monitoring. So we made the monitoring on the open and monitoring in the young forest and mature forest.